We're live now. Hey, sorry, everyone who's been waiting for a bit. Looks like we had a few technical glitches. We'll start again from the top. Welcome to the first episode of SingleStore Engineering Deep Dive. This series will run every month last Friday starting today, and we are live streaming across various channels. The goal here is to demystify the internals and take you along on a journey on how we built and are continuing to approach some of the toughest engineering challenges in building a modern database system, let alone a system that can handle transactional and analytical workloads in the same breath. Here I will introduce some of the brilliant minds that built this product and let them walk through the architectural choices, the trade-offs, and the art of the possible. For introductions, I'm Shireesh Thota, and I'll be hosting this first session. My title is Senior Vice President, and I lead engineering here. I have extensive database background all through my professional career. I'm thrilled to have two incredibly accomplished engineers with me for this episode. Adam Prout is our CTO and co-founder. Robbie is SingleStore fellow. I'll let them introduce in their own words, and then we'll deep dive soon. Adam?
Hi, folks. I'm Adam Prout, as Shireesh mentioned, one of the co-founders of, at the time, MSQL, now SingleStore. So I've been working on the product for over 10 years. Before that, I worked at Microsoft on SQL Server. So I'm a SQL database guy through and through, basically my entire career. So it's a kind of one-trick pony. SQL database is all I know.
Thank you, Adam. Robbie?
All right. Hi, everybody. I'm Robbie Walzer. So I've been at SingleStore for almost 9 years now. So I held a number of roles over that time. Now, technical fellow. Before that, I was at school, so this is my first real job. So like Adam and Shireesh, I'm a database lifer.
All right, 3 database lifers here. In this first episode, we're going to peek into the history of this company, the architectural overview, and where we stand today in our technological stack. Let's begin with Adam, who's our co-founder. Adam, please tell us, what was the vision that you and other co-founders had at the beginning of this journey? Please also comment on how it evolved since then.
Yeah, let's do it. Let's jump into it. So we have to transport ourselves back to 2010, 2011, when MSQL was initially founded. The database landscape was much different than today. So the LAMP stack was kind of the dominant web stack, right? I don't know how many people even talk about LAMP anymore today. Linux, Apache, web server, MySQL, PHP. And there was an architectural shift going on around web scale. This was kind of the peak of the Gartner hype cycle, if you will, of web scale. It hadn't really delivered yet. This is MongoDB, Cassandra, NoSQL. It had just really blasted onto the scene. And kind of the prevailing wisdom in this era was, sure, start with your LAMP stack. And if your app takes off, you're going to have to re-architect it. You're going to have to introduce memcached. You can maybe switch to Mongo. You introduce Cassandra. You have to switch away from a SQL database. And it's because there was no real distributed scalable SQL databases in that era. If you look at what was available, they were the data warehouses. This is Vertica, Greenplum, Astrodata. This is the old data warehouses. Snowflake and Redshift didn't exist yet. BigQuery didn't exist yet. So what we were looking at here is kind of saying, okay, we don't believe this to be true. We don't see a reason to switch to kind of less featureful systems. Obviously, memcache is a much less featureful system than SQL database. The same with Cassandra of that era. There's no reason for this. We think we can make scalable SQL databases that you can run your app on. And so that was the first premise. But once we kind of decided, okay, we want to do a distributed SQL database, we needed to find some place where we could get a beachhead. Because again, in that era, like if you look at today, most of the database startups start with open source and then build a managed service. That's kind of the common pattern in the last 3 to 4 years. Back then, open source was not a proven business model, not for databases. Like obviously Mongo was there, but Mongo, the company, was tiny in 2010. It was not even called Mongo, it was 10gen or something. So we wanted to instead try to pick a position that we thought we could have a 10x architectural advantage and go after big customers, go after enterprise customers. And so the spot we thought we could build that advantage was in-memory OLTP. So this is kind of based off this famous paper that was out well before that. I think this is a Stonebreaker paper from maybe 2006, 7, 8, somewhere in there. It's a very famous paper now called The End of an Architectural Era, like Time for a Complete Rewrite. If you don't know Stonebreaker, he's a Turing Award winner, and like he started many database companies, Vertica, OLTP. I'm probably going to miss 3 or 4 others, Streambase or something.
Yeah, so I think one also created Postgres.
Right. Okay. Postgres. Right. But if you go back far enough, he was in his younger days. Postgres.
Another minor addition. Yes.
Yeah, small one to miss. But he had this famous paper saying, hey, now that memory sizes are getting much bigger, disks are getting faster, networks getting faster, the SQL database is designed in the 80s and 90s. Their design decisions no longer make sense. And so there's room to do substantially better. And so in-memory OLTP was kind of based off some of the stuff in this paper saying, okay, if you build indexing that's memory only, you can cut out like a lot of the overhead of what normally happens in a SQL database with disk-based indexing. You don't need a buffer pool. The durability model is a lot easier. Like most databases that are B trees are based off arrays for durability, and it is very complicated, and it's not slow, but it's hard to make fast. Where if your data exists completely in memory, your durability model can be much simpler. You can just kind of have a logical log stream, and on recovery load it back in. So you can make your durability story faster. You can make your indexing faster. And then we also decided to bet on code generation, which other databases had already done at that era, but not to the level that we took it on. We do like code generation for everything. Like it's not just expressions or pieces of query. Like it's complete query code generation. This is compared to interpreters, or like if your MySQL or Postgres. When you run your query, you run expressions. It's basically like an interpreter that's trying to go through and run your query versus running it through like a big iron compiler. And we started with GCC originally, and now we use LLVM. But these things are much better optimizing code than anything built into a database. And so we wanted to bet on that, and that can give you like 2 to 5x performance advantage. So that's where we started. We started in-memory OLTP, MemSQL, 10x architectural advantage. Let's try to sell to big companies. We also kind of bet on MySQL, which is maybe something that's, it was some debate in that era, in the sense where MySQL Wire compatible. Because again, the LAMP stack was the dominant stack. And like, I think most companies starting today definitely pick Postgres. In 10 years ago, it was a bit debatable which one you should pick. We picked MySQL. Again, we wanted to really, like, even today, the MySQL, like the units in production of MySQL, like if you ignore SQLite, it is by far the leader. It's like not even close to Postgres. Postgres is not close yet, but I think Postgres is picking up. But so that's where we started. As far as, I guess the second question is, how did it evolve?
Adam, before you go to the evolution here, one of the other things that it intrigued me as well when I joined the company was this choice of effectively building all the core pieces of engine in-house. So before you go to the evolution part, this is going back to the beginnings of the company, the roots of the company. What prompted you? I mean, this is interesting, right? I was there at the beginning of this 2010s and 11s, where there was a proliferation of all these non-relational databases to trade off ACID with scale. And you're right, data warehouses were truly the ones that were distributed SQL. Interesting era, interesting time, and MySQL definitely was the logical choice. I would also want you to talk a little bit about how did you choose to build all these pieces ground up instead of taking some of the off-the-shelf pieces. And of course, now there are a crop of database services products that just take on that approach. And what are the challenges? I'd love to hear about that as well before you go on to the evolution of the company.
Yeah, I think it's actually, this is another spot where it's a lot different 10 years ago than today. Like, take for example RocksDB, which is an embeddable storage engine. Like, it came out of Facebook. Facebook uses it as a storage engine underneath MySQL primarily. But now, like, basically every operational database startup that has been founded recently. I don't even name them all. They basically all use RocksDB as a starting point, just because it's a nice, solid storage engine. But it didn't exist when we started. And I think that's true if you look at across the stack, like Parquet didn't exist, Orc didn't exist. So I think today you have a ton of options that you didn't have 10 years ago. That's I guess the first thing. Now, the one tricky part is obviously Postgres existed 10 years ago. And one of the problems with picking MySQL over Postgres is MySQL is GPL. So like we didn't want to be open source. So either you have to pay Oracle or you have to write all the code yourself to like the MySQL wire protocol code. Postgres did exist. We could have just taken Postgres. But we thought the MySQL wire protocol was of such an advantage that we should still write it ourselves. That was one of the trickier parts. Like that's like all the databases of that, like Vertica was, I believe, a Postgres took the code. I think Astrodata did too.
Yeah, and Parexel and then Redshift.
Parexel, right? Redshift. So like all of them were taking Postgres. So like Postgres was something we could have taken, but we decided, it's like the MySQL. We thought it was valuable enough that we should write it ourselves, like the wire protocol and all the compatibility pieces, which was a lot more work probably than we realized. Maybe if we realized how much work it was, we would have chosen Postgres. But that's the first point. The second point is, I think, taking off-the-shelf stuff. Like how many of these database startups that use RocksDB actually is RocksDB actually optimal for their use case? It's like kind of debatable, right? They just take it because it's there, right? And once they have it, like they're in a decision of, okay, do I keep up with head of RocksDB and keep pulling the code? Do I hard fork it and make lots of changes and then I'm it's not really RocksDB anymore, but I use it as a basis point. And so I think it's great for accelerating, but like you get this midlife crisis where like, oh crap, now I want to make lots of changes to this open source thing and I don't know the code. You want to jump in?
We have taken open for check search use Lucene, which is to get us to search a lot, and it doesn't really approach the memory model. It doesn't use, so like over time you still have to go back and make it more single store, make it what you want it to. So I think it accelerates things, and I think you're like now across the different people might accelerate, but you still have the way you want it to.
Yeah, I think this is interesting, right? When you have a bold aspiration like what we have at SingleStore, if we want to achieve this real-time analytics, trans-analytical workloads, etc., it's probably near impossible to take an off-the-shelf or basically do some really bad trade-offs. So obviously, it was, I'm pretty sure, really a ton of hard work, but we're at a good place in terms of the ability to evolve in the direction that we want to. So I'm really thankful that we made that choice looking backwards. Now, going back again to the question of how do you think it has evolved, and we would let's touch upon that briefly and go into the architectural overview. Adam, could you talk a little bit about how do you feel about this journey, and how do you think it has evolved from the point where you envisioned this company?
Yeah. So let's go back to where we were. We were in-memory OLTP. Let's say it's like we've been doing this for a couple of years, and we got a number of customers. Like there is obviously a market for in-memory OLTP. I don't think it's a huge market, but it's a market. But remember, the initial goal was to get a beachhead. Like we weren't 100% sure in-memory OLTP could be the be-all, end-all of the company. We thought it would be a big beachhead. I think we thought it would be a bigger beachhead than it turned out to be, mostly because we were hopeful the price of memory would drop, which didn't really happen. Like what happened is you could get bigger memories. Like now a terabyte memory on a single host is not that unusual, which was unusual 10 years ago. But the cost per gigabyte is still kind of like it didn't really drop that much. So being an in-memory database all the way through to today wasn't going to work. Like that was very clear to us a few years in. So what we did is, so So where we started to get pull, so remember we're in-memory OLTP, and we had lots of customers that liked the ingest of the in-memory OLTP. Like you can't beat it for like inserting new data, even if you're just streaming the data. You don't have to bulk load it, like inserting in small batches or one row at a time, and being able to upsert, like if there's an existing row, update it very, very rapidly. But what they wanted to do after that like upsert workload was running, like streaming their data in, they wanted to run more analytical queries on top of it. Because remember, in this era, we only have the data warehouses, and they can't do this upsert piece. Like they're out of the picture. So people were trying to do this kind of analytical workload with their MySQL Postgres. Some of them were using MySQL cluster, and it wasn't working that well because those systems couldn't do analytics. And so that's when we started to get the pull towards what now I think is mostly called real-time analytics. At the time, didn't really have a name. It's kind of a workload that sits in between operational databases and analytics databases, data warehouses. It has requirements of both. And so then we said, okay, we're going to take this in-memory base, we're going to add analytical capabilities to it. So this is when we started adding like the legitimate query optimizer and a legitimate query execution logic. This is the stuff that Robbie spent kind of his early years kind of building this stuff all out. And the main design partner was Zynga. This is pre-IPO Zynga, and Zynga was cool, Farmville Zynga. And what they were doing in that era was kind of neat. Like they released a ton of games. Like this was when Facebook gaming was massive. And they had a platform for releasing these games. And like every game was built on the same underlying infra. And we were part of that infra to do the analytics. And so they would want to see what's going on as they're trying to tweak the game. If there's like, what were the behavior differences of the users? Are the users enjoying the game? What's kind of all the metrics for monthly active users and whatnot they're calculating. This is all streaming in live. Like they didn't want to do it at the end of the day. Like you'd look at the dashboards and they had game managers that would look at what's going on right now, and they could make tweaks and see how it modify the behavior of the users in the games. So that's where we went to next. This was kind of our beginning of our journey towards transactions and analytics and being more general purpose. And the real-time analytics piece, I think, took us very far as a company. Like this is a very repeatable use case. Like this is how we broke into banking. Like if you use a bank in the Western world, your data is most definitely in SingleStore. This is how we broke into streaming. If you use a streaming service, maybe other than Netflix, your data is definitely in SingleStore. It's also in oil and gas. Those companies maybe folks don't realize, but like that kind of streaming use case where you want to stream the data in, do some analytics. It's sometimes customer facing, sometimes internal. Sometimes the app just takes actions, like if there's some kind of a trigger event that should, they want to happen kind of promptly when the event is detected. So this is where we went to next. And that is a lot of work to build an analytics system from scratch, for an optimizer from scratch. And we probably started on that journey around the time Robbie joined.
Yeah. And Adam, I think, yeah, this is fascinating, right? Thank you so much for sharing this history and how it evolved. It's just incredible to see how the cloud trends, the database trends, the hardware trends have all converged, and they're basically part of the history, right? If you kind of really try and read how MemSQL evolved into SingleStore, you'd get a good lesson in terms of how the initial bets of the memory to disk kind of price reduction, how the trends changed, how the cloud changed, etc. Over the course of time, there have been some of the massive improvements in terms of obviously how to take a database to market in the cloud, especially the storage compute decoupling and how we commoditize the storage pieces, and how the database industry is really going in the direction of unbundling and mostly commercializing the compute side of things, especially query index, etc. This is a great midway point where we can pivot to the architectural discussion, and I'm pretty sure our audience would appreciate it if you go into some of the overviews here. So to begin with, I basically want to ask you both on the details here. Effectively, if you broadly look at the architecture and the key pieces, I find the in-memory, the column store with its unique take on the updatability and indexing, various innovations in query layers, the recent bottomless components. And these are a few of the key pillars that I view. I'd love to share I'd love to have you share your views on these big rocks and how they fit into this novel offering. So maybe I'll go to Robbie first and then come back to you, Adam. Robbie?
Sure. I'll go a little bit into some of the analytics journey and how that led us down the universal storage path that Adam was starting to allude to. So around the 2015, as we're pushing into real-time analytics, we started building out our first we had to build out our distributed query processing capabilities, build vectorization, operations on encoded data, and we really focused on that. And meanwhile, in the background, we added disk-based capability with the column store, and we really were just focused on analytics, the analytics part of the workload for with the column store at first. So it did support pretty streaming ingest. So we put our in-memory row store right in front of that is what we call like the in-memory segment to buffer up writes. But really the investment on the inquiry execution side was entirely on the analytics side. So this allowed us, we did with a partnership at Intel, did a benchmark where we were able to do trillion rows per second. We were able to get really top tier TPC-DS and TPC-H results. And so that allowed us to really grow in the real-time analytics market. But at the same time, we were also getting this push on the more operational side, where our customers would love the analytics performance and also the total cost of ownership of the column store, because it was highly compressed on resident on disk or SSDs or whatever you have there. And they would love the seekability, updatability, and operational performance of the row store. But as Adam mentioned, the memory prices, although memory capacities went up, memory prices never really went down. So to at this point in time, to really run an operational workload on what was still memSQL at the time was pretty expensive. You could make it work by combining column store and row store, and building your own like migration logic between the two in the background, and you could get really good performance out of it. But it was very complex, and so we're getting this. We could feel this push and or more pull from our customers for a while, and ultimately, after a lot of prototyping, decided that we needed. We knew we needed something better to bring down the total cost of ownership there. So we investigated whether we should bring in something external like RocksDB, or we should take what we had and evolve that into something that supported operational workloads. So one of the main reasons that we chose to evolve as opposed to bringing in something like RocksDB was that was really simplicity. That if we could take the column store and add enough operational capabilities to it, and I'll go into some of the details of what we did, and make that good enough at analytics or good enough at operational workloads while retaining the analytics capabilities and making it basically no worse, that would be way better than taking in RocksDB, which would be great for operational workloads but terrible for analytics. So the couple things that we identified that we needed to be able to do to be able to run operational workloads on the column store. So first, the most important thing was to be able to do what we called subsegment access. So in your column store, you have like a segment, and within each segment that can store about 1 million rows. And before subsegment access, and this is how most other column stores work. If you're reading a block of data, you read that entire block. So if that segment contains 1 million rows and you only need to read one of those rows, that's extremely wasteful. So we went through and redesigned basically all of our encodings. A couple of them already supported it, but all of our encodings able to support seekability. And in some cases, we did trade off a little bit of compression ratio, but to us, that was the right trade to make. The next thing is, now that you can support seekability, you need to be able to navigate quickly to where the row is. So added secondary indexes. And So that allows us to do both seeking and then use those indexes for constraint enforcements, for unique key enforcement. And finally, now that you have seekability and you need to be able to do high throughput, you want to be able to do high throughput updates. So to be able to do that, you need to be able to do row level locking. So that was the third part, the third piece of our universal storage that we built. And with that, so I think that the initial wave of that we shipped in 7.0, and since that it's been really cool to see the workloads that really just wouldn't have been possible before. Some of them you might have been able to make work, but the workloads that you can now run on SingleStore, and other cool thing that I forgot to mention. So the name of the project to build universal storage was actually originally called SingleStore. So this was we had a dual store. We had column store and we had row store. But SingleStore was going to take all of the best capabilities of both the column store and the row store and combine that into one.
Yeah, that's an amazing journey here. This is really novel in many ways. When people think about bringing the operational and analytical workloads into one place, you're effectively thinking about removing the ETL, ELT operations. But this is a holistic, really a first-class way of doing it. You basically have an operational head on top, and then an updatable, a seekable, and indexable kind of a column store. Now, in each piece, I've seen this happen in different systems. I've been part of some of the projects in the past doing some of them, but to bring them all together is incredibly novel, and I'm pretty confident in saying that this is the only kind of it, right? This is the only architecture that kind of brings all these pieces together. Zeroing in on each of these things in terms of how to do it. You look at some of the alternatives. You have an OLTP system, an OLAP system. You have to move the data, ETL, ELT. You could eliminate it at best because you could sort of think about wrapping it up. But this architecture is just novel. And I know that our Sigmod paper recently touches upon a bunch of these aspects.
Yeah, the alternative is what a lot of other HTAP systems do, and what we would have had to do if we had chosen to go with a conventional or operational workloads would have one data structure, like a conventional B tree or like workload, and essentially a CPC that's capturing the workload on that data structure and replaying that on their different systems. You have to build Optical Smarts to figure out use if you're joining, say, analytics with operational data, and that operational data hasn't been merged, so we really want to do something like that, and that's what you know HTAP systems where HTAP capability has been really built.
Yeah, no, I think this is great, right? And in fact, if you kind of think about, and I'd like to deep dive a little bit on few of these aspects, right? And maybe we start with indexing. One of the things that really struck me, and it's just an amazing way of thinking about it, is how do you, of course, updatability is a major piece whenever you have a column store. People do updatability in different ways, and we have a novel way of doing it. Indexing is another amazing piece, right? Where we have innovated quite a bit. And if you think about how we do our indexing, and I'd love for Robbie, Adam, one of you to talk a little bit about how did we do this, two-layered indexing, and how did it help in sort of getting through these benefits?
So yeah, Robbie, so what I like do the details. I can make one.
Yeah.
I can make one high-level statement. It's kind of tying back to what Shireesh asked originally, like why not off-the-shelf stuff? Now, because if you look at how this evolved, like how Robbie said, initially it was kind of a normal-ish column store with a set of compression schemes. And then we wanted to modify those compression schemes. Now imagine if we used Parquet, right? Like there's no way the Parquet folks are going to accept our modifications. And then and you're going to see here, and Robbie, you can discuss it, we need some IDs and offsets to be stored. It's not a lot of extra metadata, but again, because we can control the scheme, we could optimize it. We could optimize our storage for how we wanted it to be, like how our customers were demanding it, not just what was available in the kind of off-the-shelf component. But I'll let Robbie describe the details. He's the expert on this.
Yes, our design. It's very simple. And so it'll show overhead. So within your column table, it's made that the structure are logical segments, and each segment is going to connect a million rows. And the level of the index is we just store alongside that mapping from the key columns to the offset within the segment for those, so in a posting list. So if it's a low cardinality column, you'll have very long posting lists that are that, and then at the global level, so that helps you once you're at a segment to map to a row. No, so Adam just asked me in the background if that has a lag. So that's actually completely synchronous. So that gets written out when we write the segment originally. We will write out the index segment for that as well. And then to do global seeks, we will then create a hash table that then maps from key value to the segment that row segment that key exists, and then the offset within that segment index where the key is referenced. And so with sorry, we're going to ask a question.
Yeah, go ahead, Robbie.
Oh yeah, so
I was just thinking, Robbie, this is like I think what you're referencing here is a nested indexing, right? This is beautiful, exactly. and basically,
two levels of index, and the global index is created in the background. So you can essentially think of it where it's organized like an LS entry. Recently written data will not be merged into the global index yet, but over time the levels will be merged together. And then also, because we're storing lists of essentially offsets and location, if you have predicates that match multiple indexes, we can do index intersection and use as many indexes as possible within the query. So it's
in basically a log and hops, you would basically be able to get to the segment, and within a segment you already have an offset, so you could jump in there, and this is quite fascinating. I always get asked about the hashing choice, right? Whether given that it's not range index, what are the challenges? I think of it as basically the fact that obviously the scans are much faster. ColumnStore can really eliminate those IOs, and it's never been a problem for us in terms of not having that challenge. Do you agree, Robbie?
Yeah. So there are obviously cases where it'd be nice to have a range index, but we chose the hash index, one, because it was really simple to implement, and also that because column stores have such great scan performance, to make an index really worthwhile, you have to have a very selective query. Otherwise you might as well, you really don't have a huge benefit over just, doing an encoded scan on that column. And so, and most of the time range queries, they can be, even a moderately selective one is still probably maybe querying thousands of rows. Whereas, with the quality predicates, you could be running much more selective filters.
Yeah, so this is great. Adam, do you have anything to add? If not, I'd love to move to query part and focus a little bit on the query innovation, because there's quite a lot of amazing things that we've done there. Should we?
No, that's fine. Yeah, the one thing about the range queries too is SingleStore does have sort keys, which not every column store has those, but it's kind of a common thing. So that also helps with range queries on particular columns.
Got it. Yeah, so the next thing that I would love for us to touch upon, and this is a equally important innovation in this space, is query execution. I know that we have done, of course, when you have such an ambitious aspiration to do both operational and analytical workloads, it becomes really tricky in terms of innovating both on the compilation side and optimizing, getting data from both in memory as well as column store, etc. Would love to hear more about that. And one of you, could you please throw some light on this?
Sure. So I think, as we've mentioned a couple of times, a key part of our query execution is that all of the queries are getting compiled. So one of the downsides of that in a lot of systems is a relatively high first query runtime cost. So one of the things, we started out with GCC based cogen and then switched to LLVM based cogen, and that brought down our first query runtime costs a lot. And then the next big innovation, I think we're probably the only, there might be a couple other databases that are doing LLVM based cogen, but I don't think there's anyone doing what I'm about to mention next, is that the way our cogen is laid out is within the engine, there are a number of opcodes that engineers define. So, do a seek in a skip list, do a hash an integer, a 64-bit integer, et cetera. And those are at server compile time, either generate compiled down to LLVM IR or just standard assembly code. And at runtime, we can when we are generating a plan, we are essentially generating a sequence of these bytecode operations, and we can either stitch those ops together, the LLVM IR for them, and pass that to LLVM, who will then compile it down to machine code, or because we also could just compile the traits those each on their own, we could just interpret it and go through the sequence of opcodes in an interpreter. And so the interpreter is obviously great because it has a very low first runtime cost, but it's a bit slower. So what we do is we will start the query in interpreted mode, and in the background, LLVM will do the full compilation. And then once that is finished, we can just hot swap that in if the query is still running, and then we'll go at max speed. So that kind of gets us the best of both worlds. Some of the other
incredible, right? I mean, this is so fascinating that we've taken this parallel approach, and yeah, please tell us a little bit about the numbers and results that have accrued to this.
Yeah, so that varied from workload to workload, but I think with some we were able to drop in some cases the first query runtime cost by like 10x. So it was really huge for ad hoc workloads. So some other really important things that we've invested in were operations on encoded data. So that's really how we were able to do things like the trillion rows per second benchmark, where if you're doing a group by on a dictionary column, you can at the per segment level, you just run that group by on the dictionary itself as opposed to decoding and hashing the values. And you can use an array instead of a hash table. It really obviously simplifies the code, and you're able to use SIMD because you're just operating on simple integers.
Now, I know that there's quite a lot of detail to unpack here.
Yeah.
We are 100% going to deep dive on this on one of the subsequent episodes. Definitely will ensure that we'll look at the hot swapping technology here. But to just kind of summarize here, I think we're talking about a host of improvements here, starting from the LLVM-based code generation and how we handle the plan caching, how we do this hot swapping and basically doing compiler, interpreter, and hot swapping and putting in the plan cache, etc. And then, of course, some of the most well-known techniques in the column store query execution, vectorization, working on the encoded data, etc. But these innovations are really going in parallel at full speed so that we can do both operational and analytical workloads. And the proof really is in our benchmarks. And we would go and dig into some of the benchmarks. We'll share links. What we could do, thanks to all these innovations, we have done all these improvements so that you could do both TPC-H, TPC-DS, and be extremely comparable on TPCC workloads as well. So we've looked at storage a little bit, we've looked at indexing and the query execution. One of the next biggest pieces that I want to touch upon is the bottomless storage. Would love to get there. Maybe before that, I want to take a few questions here that have been coming in from various social media here. So the first one is asking if we can assume SingleStore is one solution for both real-time and analytics use cases. Adam, I'll let you answer this.
Yes, I think that's actually extremely common. So like usually the same data you're doing real-time analytics over, you also just have like a more classical analytics workload. Like, I could do that in an data warehouse. But why would you want to move the data to a data warehouse? So I think that is extremely common, like to do kind of classical analytics, a long time real-time analytics in SingleStore on the same data. That's definitely very common. And in fact, one of our newest features released in June, it's called Workspaces, and it's to kind of support this exact use case where you can set up a different pool of compute over the same underlying data. The data is all in blob storage in the managed service. You can set it up on-prem too. It's just so you have to use your own S3 bucket. And you can kind of spin up compute, say, here's this analytic workload, maybe it's a reporting job. Over the same data, I can put it in this compute, and here's my real-time analytics, maybe customer-facing, can never go down. It's in a different set of compute over here, so that you can kind of enable that use case and not kind of worry about your analytics use case, your classical analytics use case kind of interfering with your real-time customer-facing analytics that's maybe coming up through an app. So that's very, very common among our customers.
Yeah, so the next question, I'll just read it. I'll maybe paraphrase this a little bit. I think the question is asking if they have, the classic practice is to collect the data from different systems, create a data lake, let's say an S3, an AWS, and then build data warehouse in some of the known data warehouses like Redshift, for instance. So the question is, if you plan to use SingleStore, can we assume that they could avoid multiple hubs and have one system fulfill all of the storage, processing, data mart, warehouse requirements? Go for it, Adam, once again, or Robbie, one of you.
Yeah, I think it's a little tricky because although we call ourselves SingleStore, that doesn't necessarily mean every possible database workload in the world should run on SingleStore. So I would say if you have a data lake, like it depends on the amount of data you're storing in it. But if you're storing like petabytes and petabytes of data, like SingleStore is probably not the use case for you. If you don't have any kind of operational like application level requirements for that data, most likely like you can still do it. It's probably going to be fine. It's just not. It's not what we would design for. Now the data mart aspect, like if you're like that part, we're like data mart versus data warehouse, like those two are so close together. Data mart kind of the more operational aspects, serving it up to more customers. Like that part is very, very common. But yes, if it's just like a classic data lake, that's not a spot we typically play. But data mart, data warehouse, if you have some kind of SLA requirements, whether it's like a throughput SLA, like you need to support X customers, or a latency SLA, like you need this dashboard to load in X milliseconds. Those are the key use cases. If you have something like that, that's typically where we shine. And then if you have that and you add it in, say, hey, just normal analytics on the side, we're also good at that. Like that's those benchmarks Shireesh was mentioning, that everyone was probably aware. I don't know everyone, but like people in the database land, like Databricks and Snowflake throwing mud at each other over TPC DS. That's probably the trickiest analytics benchmark, classic data warehousing benchmark. And you can go on our website and see our results, right? It's at the smaller sizes, say tens of terabytes, where like more typical data sizes, we're typically faster than those systems. So just for the query part, right? The select query part, we obviously dominate them on the write performance. Like those systems can't really do writes.
Yeah. So, I mean, to kind of summarize again, the key thing, I keep getting asked this question a lot. There's the iPhone analogy. I'm pretty sure you've heard it in multiple contexts, but I love that analogy, and that applies here quite a bit. When you think about the amount of use cases that exist in big data and the data processing, you basically have some of the pure operational single node kind of operational systems where you're probably happy with single node MySQL, Postgres kind of thing. And then on the far right is the really big data where you're trying to run queries that run longer. You have to spill the query state itself to disk because the query itself has to run longer, and you're dealing with hundreds of terabytes to petabyte ranges, etc. So you have this classic where you need to decouple the storage and compute, and you can build applications on that side. And then there is a whole lot in between on this spectrum where you basically are trying to go distributed for the modern applications. The modern applications are no more those kinds of applications where they're just looking for a simple operational SLA or a simple analytical, dashboard kind of a thing. They really need to bring both of these things together. And this is where the iPhone analogy comes handy. When you are looking for, let's say, a industry grade kind of a camera, you probably are looking for, let's say, nature photography or something like that. You probably are going to need a DSLR kind of a camera, but most of them don't, right? Most 90% of the applications, 90% of the use cases really are happy with the 12 megapixels on my camera is plenty. That is the analytics, user-facing analytics, the customer-facing, modern interactive analytics with SLA, where you want to build an application that has the analytics in place, where you don't have to really go through this complex architecture. And those are the use cases which are growing and are probably going to be the most number of the use cases. That's where the distributed SQL systems and the trajectory is headed. And SingleStore shines significantly in these use cases. So yes, there is a place for the single node databases. There's a place for sort of like the full-blown decoupled, really large data warehouses. Most of the use cases are in between though, which are modern, which require the real-time analytics with SLAs. You want to build applications and analytics in the same place. And many of our use cases, if you go to our website, they speak to that, and that's our strength, right? And to solve them in the traditional way, it's just wrong. It's too complicated, right? And that's kind of really where we are headed. Let's go back to one of the most important innovations that we've done in the recent times, which is bottomless. Now, this is where you would see all the classic data warehouse systems tout the decoupling of storage and compute. And of course, the convergence, the technical convergence of cloud definitely enabled it. But that comes definitely with a lot of advantages. Decoupling it will help quite a bit. But it also comes with a lot of challenges. Writing it inline into an object store is not great, etc. So I'd love for us to spend a little bit of time on how we have envisioned and architected our bottomless, and maybe we'll use this picture here to kind of point out, and then we'll spend. I'd love Adam, Robbie to touch upon what is that we are doing differently vis-a-vis this object store.
Yeah, I can start with this one, I think. So if you look at separation of storage compute in databases today, there's kind of like what the cloud data warehouses do, and they all do more or less the same thing now, which is if you write one row into a cloud data warehouse, that cloud data warehouse is not going to tell you it's a committed row, like respond to you, say, hey, I have that row, until that row reaches all the way to the blob store. Like both Redshift, Snowflake, and BigQuery all do this. And so obviously this is fine if you're bulk loading, right? If I'm loading millions of rows at a time, this kind of latency hit of having to batch them up and hit the blob store, like S3, not that bad. If you're just loading a few rows at a time, this is a disaster, right? This is basically a disk that is, if you're lucky, tens of milliseconds of latency. If you're unlucky, seconds of latency to each commit. And so for us, because we want to support this, the real-time analytics, right? The streaming ingest, you can ingest a few rows at a time in millisecond latency. When we were doing separation of storage and compute for SingleStore, that wasn't going to work. So then if you look at what the operational databases do, and that's kind of Amazon Aurora is the classic example of this, and everyone copied Aurora's design, like Microsoft is Hyperscale, which is more or less the same thing. And Google finally, very, very lately, just announced theirs like a year ago. I forget what it's called now.
Alloy DB.
Alloy, yeah. But they all do the same thing. They basically take the log processing chunk and say, I'm going to put that in a separate service. And kind of a bit of the, depending on the system, they do the the buffer pool chunk in a different storage layer, and then each of the compute nodes just have to run queries and grab things from that storage layer. But in those designs, the local disk must match the size of your storage. So they always have maximums. Like if you look at Aurora's, it's pretty big now. I think maybe it's even measured in terabytes now, but it always has a maximum size. But it doesn't have the latency hit of the blob store because it's kind of like an EBS like storage that's aware of kind of the log stream that's hitting it. It's like a fast EBS. But for us, since we have kind of operational analytical kind of components, what we did instead is to combine durability on local disks with the blob store. So like when you write a row into SingleStore, I'm not sure if we have a slide that shows this somewhere, but like it's going to commit on local disk first. So you still have the normal speed of your local disk when you're writing just a few rows. Asynchronously, it's going to batch those rows up and push them to the blob store. And what this means is you kind of get the best of both worlds to some extent, because you have your low latency writes and you have the separation of storage to compute of the blob store, because we don't have to keep all data on local disk. If you're not querying it, it'll get pushed to the blob store and removed from the local disk. The blob store is still eventually responsible for durability in HA of that data. But while it's hot, while it's being written recently, it's still on local disk. So you kind of get the best of both worlds, and you can still get all the benefits of like a cloud data warehouse. Like you can still do point in time restores out of the blob store data, which is great because now you can store months of history in the blob store basically for free. Like S3, if you're not touching the data, is very, very cheap. And so you can kind of go back in time to weeks ago if you want from the blob store. It doesn't have to be on local disk, and you can spin up new compute. Like I was mentioning earlier, the workspaces pieces, you can spin it up from the blob store. You don't need to touch that kind of, they say that real-time ingest cluster that's like super mission critical, and you want to spin up your analytics cluster. It can be spun up from the state in the blob store. It doesn't need to bother your production kind of ingest cluster. So that's kind of how we took pieces of what the cloud data warehouses do and a little pieces of what the kind of the Aurora type design does. I didn't talk about the Aurora type design, but the logs are also flowing. Like the transaction logs are also flowing to the blob store, similar to how Aurora pushes theirs to a storage system. So it's kind of taking pieces of both of those designs to come up with something that overcomes the disadvantages of both of them. Like the disadvantages of the operational system is that it's not actually unlimited storage. And the disadvantage of the cloud data warehouse is that every write hits the blob store immediately, so your latency is impacted. We don't have either of those problems. So,
thank you, Adam. That's quite an amazing description of our challenges. I consider the decoupling of log approach that Aurora and Hyperscale or AlloyDB, etc., as like 0.5x distributed system. It's not a full distributed.
Yeah, exactly.
you could really scale your reads with an eventual consistency effectively, but you really can't scale writes. And I think shared nothing architecture is something that we embrace fully. And the bottomless, it's beautifully named. We call it unlimited storage. It really helps. And I guess there's a question on, is it really unlimited? I think it's as unlimited as the object store offers us, right? There are definitely some of the tunings that one need to be aware of in terms of what happens when you're trying to. There are some implications in terms of your compute to storage ratio. If you're trying to do your workload requirements could impact it. But from a notion of archival, tiering to cold storage and keeping a cold, warm, hot, etc., all those knobs beautifully exist and they work very well in this architecture. And as Adam explained, we don't impact the write path, etc. The disk effectively becomes a write-ahead cache. If it exists, we use it. The bottomless, if we don't, it's fine. It's well designed in that sense, where it uses the decoupling of storage and compute, and yet serves the modern analytical use cases. So, and these are some of the key topics. As I said at the beginning, I assure you we're going to go into a lot more details about each of these topics. We are top of the hour. I think at this point, I'd love to wrap it up and thank my guests here. It's just an amazing details and a significant amount of technical overview has been shared here. So thank you, Robbie and Adam, for your insights and deep expertise. Any final words before we wrap it up, Adam?
No, thanks for hosting.
Robbie?
Yeah, thanks. This was fun.
Yeah, so thank you, everyone. We are excited to kick off this journey again. We are planning to bring in many of our other engineers to walk through the details for engine, infrastructure, and even our managed service. So we have many offerings. We're going to go into all these details. Please send us questions that you may have about our technology. Of course, we welcome feedback on tuning this content. We definitely are looking to adjust it based on some of the interests that you have. Yeah, so this is going to be last Friday every month, and we will evaluate if you to increase the frequency of this. So till we meet next time, goodbye. Thank you.